Okay, if you are watching this video, it means that you are getting ready to start working on the greenhouse gas lab. And I just want to cover the first part of this before I let you go do the PhET simulation. So you can see, like, obviously I'm on the OneNote page right now, and this is the PhET simulation that you're going to be using. By the way, I think it's much better if you click that link instead of trying to use the embedded version that's in the notebook. Just a tip for you. You can see on this, like, there's going to be different types of energy that you're going to look at during the lab. So there's the yellow lines and there's the red lines, and those are both representing different parts of the electromagnetic spectrum, different types of energy. So before we write anything on this page, I just want to remind you of what the electromagnetic spectrum is. Is this all the way zoomed out? I think so. You may have learned this at some point in physical science or in chemistry, but basically, not all light is the same. So, like in the middle of the electromagnetic spectrum, you've got visible light, and that's what we can actually see. But uh, just because you can't see a certain type of light doesn't mean it doesn't exist. So you can see on the left side of this scale, you have things like radio waves, microwaves. Those are really long wavelength types of energy. On the right side of the scale, you have X-rays, gamma rays, way higher frequency wavelength. And so typically what we say with the electromagnetic spectrum, higher frequency equals higher energy. Lower frequency equals lower energy. And that all has to do with the wavelength. So you can see on this scale, you've got infrared light and ultraviolet light. Those are going to be the types of energy we're talking about in this lab. So infrared, ultraviolet. Okay, I'm going to hop back over to the notes now. In general, because in natural resources, we're not getting too deep into the physics of it. So when I say light, what I really mean, oh, hang on, I gotta get my drawer up. Hold up. What? Okay, sorry. When I say light in this lab, what I really mean is UV radiation. So this is like the incoming UV energy from the sun, and we call this shortwave radiation. And we're going to draw a representation of that. Shortwave means a short wavelength. The shorter the wavelength, the higher the frequency, because that means, like, as this wave is moving, it's going to hit something more frequently. It's like getting punched in the face 12 times per second versus heat is going to be much less times per second. So shortwave energy, higher energy, more frequency. Heat is generally going to refer to infrared radiation. And this is known as long wave radiation. Long wave radiation has longer wavelengths, less frequency, because as this wave is moving, it's only going to hit you in the face like 3 times per second versus the UV radiation. This is all on the electromagnetic spectrum, but something that's important to remember is the sun emits everything on the electromagnetic spectrum. We also emit some types of energy on the electromagnetic spectrum. Like humans emit infrared radiation, but we do not emit UV radiation. So all living things, and honestly, non-living things, emit infrared radiation. It's basically just the heat that radiates off of them. And that's what you're seeing whenever you see like a picture of a person through night vision goggles like this. What it's picking up is the infrared radiation being radiated out of them. This person is not giving off UV waves because only the sun does that. Only really high energy bodies do that. But people will emit infrared radiation. Same as like the Earth as a whole has an infrared signature. If you were to leave the atmosphere, look back at the Earth using night vision goggles, you would see a picture that looks something like this. And also, what's interesting here, you can see the trends that we've talked about before, where the poles are typically going to be a little bit cooler, therefore they're not emitting as much infrared radiation, and the equator is a lot hotter in temperature because it's receiving more ultraviolet radiation from the sun, it's receiving more incoming energy, and so therefore it's going to heat up more and be re-emitting back more heat. So everything has a heat signature. Everything gives off infrared radiation. That's something that's going to be important for you to know as you go throughout this lab. One last thing we want to talk about is the term greenhouse gas. A greenhouse gas is an atmospheric gas that regulates temperature. Really, it regulates the Earth's temperature. So it's a global thing. Like it regulates the whole Earth's temperature. And there are several examples of greenhouse gases. I'm going to have to write this. Probably we'll just write it underneath because there's nothing else you need to put in that space. So examples, CO2, which is why you're doing this lab. CO2 happens to be kind of the main character when we talk about greenhouse gases, but it's not the only one. Water vapor is also a greenhouse gas. Water vapor also works in the atmosphere to regulate temperature. And methane is another really common greenhouse gas. So collectively, these gases work in the atmosphere to regulate our temperature. They are not bad things. In fact, if we had zero greenhouse gases, the Earth would be like we wouldn't exist. There would be no stable temperature on Earth. It would be searingly hot or frozen solid, and there would be no stability in climate. So greenhouse gases are really essential for the function of Earth and the stability of our climate. So in this lab, what you're going to do is experiment with different levels of incoming sunlight, like UV shortwave radiation, and how that affects outgoing long-wave radiation from the Earth. And then what you'll do is you'll change the amounts of greenhouse gases in the atmosphere and see how that affects incoming UV radiation and outgoing long-wave radiation.